بلاش. السلام.
Are you recording?
Sorry?
Are you recording?
Yes. See the red dot?
This is for recording?
Yes, for the recorder. Questions from last time? Guys. لا أنت حسين. No. When have you registered to the class?
Last week.
I saw your name from the first day. Why you are not here?
I am coming Monday. Sick.
Okay, you have three already missing lectures.
Sunday, Monday last week.
No. Sunday, Monday? We have only Monday, Wednesday. Because I like to have you always here. مسكين واضح انك مسكين. Yeah, good. Questions from last time? Sure. Last row. All clear? Sure. No comments from last time. Let's make a small review. So I think it was this one. This one? What is this? Yeah, good. Okay, so last time eventually from the beginning of the semester, we have seen the source encoder. What is the role for the source encoder? Okay. The source encoder is in charge of transferring or transforming the samples into bits. How? We have something called fixed source encoding, which is the easier way to do it. 3 bits for all, 2 bits for all, or whatever. The other one is to make it variable. Variable based on what? Okay, so we have seen the entropy and we based our variability based on the entropy. So how to do it? Last time we saw this Hoffman code. We saw the steps and we achieve what is the best code. I repeat, best code does not mean that the efficiency is 100%, but yeah, it is the best code achievable. If you would like to increase, okay, this maximum achievable efficiency, we have to change something, okay, in the source, and this is what we call the extended source. So instead of one sample at a time, we take more than one sample. And we saw this way that will increase the efficiency for sure, but yeah, it will have a drawback, which is the delay. And we stopped. Sure, no questions? All clear? Good. So what's for today? I see that you have already written here the title, okay? Quantization. So this will be the first stuff that we will discuss today. So what is quantization? If you would like to define it in terms of words, so here it means approximation. The quantization is an approximation. Approximation what? This is what we will see. And where is it used in engineering? So far, we always started that. Okay, let's repeat what is the procedure. So the procedure is like this. We have here a voice signal, for example, any analog signal that comes like this. Okay, here this is time. Here this is its amplitude or power, wherever you would like to put it here. Okay, power and time. How many samples? Infinity, 100 million samples. You are talking 2 minutes, 3 minutes, 1 hour on the phone. It will continue sending samples. But these samples that they are sent, what are their amplitude? Abu Asad, what are you doing? Come here. So what are the amplitudes for these ones? Okay, we know that this is the sampling. How to do sampling? You have learned that there is something called Nyquist. What is Nyquist in charge? It will tell you each one you should take a sample, each 1 millisecond, each 1 millisecond, microsecond, 15 milliseconds, and so on, based on what is the frequency. Okay, you multiply by 2, and if anything larger than that is enough so that you can fully recover the signal at the receiver. You can revert this operation. Cool? This is what you have seen from Nyquist. The issue is, what is the value for these ones whenever you will take them? So here, this could be, whatever is the value, you go to the oscilloscope and you take points, and whatever is the value. So here, this could be 0.51, 0.74, 0.98, 1.301, and so on. What are the different values? How many different values, amplitudes we could obtain? Anyone, because there could be any value. So here, we could face or could have any amplitude. If we have any amplitude as a value, okay, let's go back here to whatever we have seen. How many values we have here? 7 different values. How many values we have here? 5 different values. Right? You see here? So we have 5 different values, 7 different values, extended 9 different values. Here we are saying that you can have any value, infinity. Even if you go for the easiest encoder, what is the easiest? The fixed encoder. In the fixed encoder, the number of required bits equals log 2 the number of samples. So log 2 of infinity, how much is log 2 of infinity? Infinity. And we know that there is nothing called infinity in practical systems. Okay, you cannot never implement infinity. Right? Infinity is a pure math, okay? Indication of something that is very large, but in practical life, there is nothing called infinity. So how we will implement infinity bits? We can't. So here, non-implementable. So whatever we have discussed so far, that we have a continuous signal, we make sampling, and then we will put it into the encoder, actually does not work. Okay, so just revisiting whatever we have seen, it's impossible. Therefore, we need some intermediate step. I want to talk to you after class. Okay? So we have here then the operation or the chain that we have seen. It has sampling. Then some intermediate step that we will see now, the quantizer. This is the reason here. And then we will have the source encoder. So what is this quantizer? What is it in charge of? We said this is approximation. Approximating what? Let me change the color. Because here we said that we could have infinite number of amplitudes. We have to restrict these amplitudes. How to do that? We will say that all the values between 0 and 0.5, we will approximate them to be 0.25. All the values between 0.5 or 0.75, no, 0. And 1, we will say that they are approximated to be 0.75. All the values between 1 and 1.5, we will approximate them to be 1.25. This way, okay, we will restrict the number, okay? Instead of having infinity, now we will have 1, 2, 3, and all the values larger than 1, whatever is the value, we will say this is 1.75. So here, for this case, an infinite number of possible amplitudes, we transform them into only 4 different amplitudes. This is the kind of approximation. Definitely, you will say, come on, you have a huge loss, because here, the value of 1.51, 1.52, 1.53035, whatever, up to 0.9999, all of these values, you are dealing with them as they are equal, and instead of that, you are assuming that they are 0.75. So you have a loss. Okay, so here, this quantization, definitely here, it will induce loss. That is the drawback. So let me repeat. You can write, then I will talk.
For the amplitudes.
I will repeat now.
How much loss are we getting with this?
But now we will quantify.
Error there?
There is something called quantization error. شو مالك ابو الخل؟ All good? ان شاء الله. as you wish. We can. So let me repeat. We said that here, and this is we are repeating the procedure. The procedure is we have a continuous signal, that one that is in blue, okay? And the first thing that we do sampling. You have seen Nyquist and all the stories, okay? So Nyquist is telling you on this axis what's happening, how many samples per second. This is why the Nyquist metric, okay, or unit was how many samples per second. So it is telling you need, in order to recover the signal, is not enough with one sample here, one sample here, one sample here. You need to take more samples. How much more? This was the role of Nyquist. So how many samples per second? But it never told you what's happening on the y-axis. It's only telling you what's happening on the on the x-axis. Okay, you need 1,000 samples per second. You need 20,000 samples per second, and so on. Samples per second, the unit. Amplitude. What was the value for each sample? I don't know. Okay, you have not seen that in signal and system. So here, all of these blue dots. This is what Nyquist is telling you. This is inside sampling. Good. Thank you. So sampling is good. We got out of the sampling. The source encoder. Here, whenever everything that you have learned so far, always I was giving you the samples. I was telling you have 7 samples. You have 5 samples. You have 9 samples. Okay? Where are they coming from? I told you this is from the sampler. Now we are coming to discuss more in detail. Okay? Here, out of the sampler, I could have an infinite number of amplitudes. Okay? So I could have infinite number of different samples. Okay, while on the examples we have seen, I have only 7 different samples, 5 different samples, while here it could have infinity. Okay, so if I got with infinity inside the source encoder, the source encoder will not work. Why? Just applying the easiest, okay, on the fixed one, you will need infinite number of bits. Even if you do Hoffman, you will need infinite number of bits. Good. Based on that, we need a solution between the output from here and the input going in. What is that solution? This infinity we should get rid of. Okay, nothing works with infinity. So what is the solution that came to their mind? Okay, let's approximate. So instead of having all of these amplitudes, can we approximate them to only 4 amplitudes? Imagine color-wise. Okay, you have in real life the colors are infinity. Okay, or 1,000 million colors. If I would like to send, I will tell you. يعني don't tell me والله يعني orange. I have standard colors, 8 colors, black, red, green, white, no more than that. And don't tell me, well, this is blackish, or greenish, or كعكبانية. Okay, I don't know. Okay, give me standard colors. So this is the same idea. I'm giving here 8 possible options. So here, all the amplitudes, only we have 4 different amplitudes. This is what we call quantization. So the quantizer here, we have an infinite number of amplitudes as an input. It will give us a restricted number, n number of amplitudes. This n could be 100, but it's fine. I will work with it. It could be 1,000. It's fine. I will work with it. Okay, but it has to be specified. Okay, not infinity. Clear? Clear the motivation? Good. So now, the first question is, definitely this will induce a lot of error, right? Let me put it as an example. If I have my data is between -5 to 5, and I would like to quantize, okay? So here it could be -4.9175, -0.174, 3.1101, whatever is the value, an infinite number of options, okay, between -5 and 5. What I can do, what I will do is, let me clean here this issue, and I will say that all the values here, I will divide them into 10, okay, intervals, let's say. So between -5 and -4, -4 to -3, -3 to -2, and so on. So I will have 10 intervals. They are called, in the book, they call them quantization levels, or quantization intervals, or quantization steps, whatever. But yeah, in the book, they call them quantization levels. So here, all the values between -4, -5 to -4, I will approximate them to what? Always we take the intermediate one, -4.5. All the values between -4 to -3, -3.5, and so on. Good. How much is the error? Maximum error that you can have from this procedure? 0.5. So here it could be the value -4.999 to -4.5. This is here error, maximum error, 0.5. Here the same, 0.5, and so on. I can do it another way. So here, let's say 5 intervals only. 5 intervals. So from -5 to -3, I will approximate to be -4. From -3 to -1, I will approximate to -2. From -1 to 1, I will approximate to 0. And so on. How much is the maximum error here? Here I could be unlucky. This is -4.9999. It is approximate to -4. So here it is 1, 1, 1. Based on that, which option do you prefer? Option, let's say A, or option B? The less error. So well, you have to ask me, based on what? Okay, what is best? There is nothing called this is the best. Yeah, best in terms of what? Okay, in terms of speed, in terms of if you compare to cars. Okay, well, the Porsche Carrera is the best. Yeah, but if I took it to Sea Line Beach, it will not work. It's not the best. Okay, so best in terms of what? So here it is the best in terms of the error. I will tell you B is worse than A is better. Okay, but we know in engineering that there is nothing perfect. Okay, so you improve in something, you will decrease the performance in something else. What is that? Well, I will stop here. Then you think and you can write. I see many people writing. I will shut up for some 10 minutes.
In terms of loss, in terms of noise loss, is it better? Obviously.
I will come now. This one. Khaled. What's your question?
How did we get -4 -2 0 between them?
I will answer it now again. Done? Writing? Can we continue? Okay. Let's first of all, why I decided 10, I don't know, as an example, or why 5 also as an example. So here, this is an interval of, let's say, 10, with from -5 to 5. So I said 10 intervals so that they are integers, okay? And here, why I decided -4.5, this is the intermediate. This value will achieve the least error as an average, okay? Here the same, between -4 and -3, -3.5. So always we take the intermediate. So in between -4 and -5, I would select this, and so on. Good? Here the interval is larger. So it is 2 units. This is why it is -4. Hussein, this was your question? What was your question? First of all, answered? The error, okay, I will come. So now how much is the error here? I will compare what is the worst kind of error, the largest possible. So here -5 to this value, 0.5 is an error. And I don't put minus 0.5 because the error is always absolute. Good. Here, this is -5 to -3. If I take the middle, it's -4. The worst case from this value to this value is also 1. Notice that if I change based on the request from your colleague, so here imagine that I decided that from -4 to -5 to -4, I decided to make the approximation to be -4. How much will be the maximum error? 1. Okay, so here it could be that you are at -5 approximated to -4, then the error will be 1. Okay, this is why we always select the one in the middle. Good.
What's written above the quantizer Q? Induced loss?
Yeah.
Induce, this quantizer will induce loss. This is your question, right? How much loss? I will come now. Well, so far, how much loss? We know it. How much loss in terms of numbers? I will come later to it. Someone else, yes.
Value of 4.5, you pick it or just value in the middle? You can just choose what value you want.
This value?
It's just 4.5, yes.
Yeah, it's always in the middle. Well, I will come later. Maybe it could be not in the middle, but the most typical case, it is always in the middle. More issues? Clear so far? Yes.
What do you mean?
Induced loss, you see here. So we have a loss. Before here, this system, the sampling, whenever we have a signal that is analog, if we do it with Nyquist, it will be perfect, no loss, 100% correct. Here, the source encoder, we have a number of amplitudes, we transform them into bits, perfect, 100% correct. But this quantizer, we will have an infinite number of amplitudes, we will have 10, 100, whatever, so we will have some loss. This is why here I put it will induce some loss. Clear? More issues?
What if the range of like the number increases? Then the middle, like for example, from -100 to -50. We will choose the middle.
Always we will choose the middle. After you can normalize. So if I tell you, well, it is from -13 to 3. So push it to the side. You know that from -13 to 3, there are 16 units in between. Divide them how many levels you want to put. Answer?
When I increase the number of levels, it's going to decrease.
Yeah, coming. Don't worry.
We choose the
Sorry?
we choose our own interval or
I'm coming now. Just steps. Good. So first of all, oops, new set of slides. Or I add blank when that. Okay, good. So if now which is better in terms of the error? 10 intervals or 5 intervals? 10. So here, this is here better in terms of error. Here we have less error, right? So increasing the number of quantization, I can write it here. Increasing the number of quantization levels will decrease the error. This is good, right? Always we want to decrease the error. But also we said that there is nothing for free. And this is what is best for engineers, right? Why it is the best for engineers? Because they will solve the problem. Okay, because here, if the answer is known, so increasing the quantization levels will decrease the error. So that's it. Okay, then your manager will not need you. He or she is not stupid. They will go to Google. They will search. Increasing quantization level is good or bad? It's good. It's good. They will not ask you. They will not hire you. Even now, if you go to ChatGPT, okay, you will say increase the number of quantization level is good. To tell you, some people say it's good. Some people say it's not good. So who will decide? Me, you. You as an engineer will decide, okay? Because the engineer is the one in charge to tell to the manager or to the company, based on our scenario and on our application, this should be the number. Good? Okay. Then here, this is why it's not always good to increase the number of quantization levels. What is the drawback? No. No. So what?
Same, before it was infinity, now it's maybe also infinity.
But yeah, whenever they are large, so what? Whenever we increase the number of quantization levels, definitely here we will have more samples, right? Whenever we have more samples, even if you'd like to use the easiest encoder, number of required bits, it's written here, where is it? Number of required bits equals log to the number of samples. So here, whenever you increase the number of samples, you will increase the number of required bits, right? Do you agree? Whenever you increase the number of required bits, you will increase the required data rate. We solved this example at the beginning. You remember whenever we said it is 15 kilobit per second, it is 9.3 or whatever kilobit per second. Increasing the number of required bits will increase the required data rate. If you increase the required data rate, it will increase the cost. Why? You will contact Ooredoo or Vodafone saying that, well, we need the data rate of 25 kilobit per second. Well, we need a data rate of 1 megabit per second. So you have to pay more. So increasing the number of quantization levels, yeah, it is good for error, but be careful because it will also increase the data rate requirement. It will increase the cost eventually and so on. This is the... Okay, good. Write down. Hisham, answered so far? Answered so far your concern? More concern? Sure? Okay, I will stop. وين رايح يوسف؟ انت ليش غيرت الفريق اليوم؟
بلعب على هي. وهي
Good. Good. Can we continue? Okay, good. شكلك زهقان. Okay, good. So, what I was saying. Oh, okay, good. You have heard about 4K, right? What is the 4K for TVs and so on? What is the 4K? غالي أكيد. Why? استنى شوي خبصت الدنيا لأنك. Okay, good. So what is this 4K? Why they call it 4K? This is the image. Well, this is matching whatever we are studying. Okay, this is the image. It is an analog image. Okay, so in order to transform it into samples, first of all, what they will do? You have heard about pixels. So what is the pixel? It's the sample. So the name pixel is equal here. Pixel is the same as sample, but yeah, sample whenever we design it, pixel whenever we want to sell it to people. Okay, so here the number of pixels. So how many samples are you taking for this image? So what is the number usually if you even for the screen of your laptop, okay, or your desktop or whatever, okay? What is the resolution for the screen? Maybe it is, I don't know, 1920 by how much here? 680, whatever. Yeah, there are so many options, okay? So what is this number telling you? How many samples? So here, this is one sample, another one, another one, another one, and so on. So whenever it is 4K, what does that? Here it is 4,000. This is why it's called 4K. Well, actually, it is not 4,000 exactly. It is 3,820, I guess. Okay. So, but yeah, they call it the 4,000. So there is something more than 4,000. The 8K. Yeah, is there 8K now that you can buy? Yes. Who said no? Who said no?
There is also 16K.
16K you have to pre-order. Okay, but yeah, if you go to Virgin, okay, there is the 8K. You can just grab it and buy it. Okay, so the 8K they are almost 8,000. So increasing this number of pixels is good or bad? Increasing the number of pixels. Just wait. Definitely more resolution. Whenever I say more resolution, what does that mean? in terms of error? Less error. So here, this is whenever we are saying here that we will have less error, this is the more resolution. Why is that? Whenever I make a picture, okay, real time, okay, we have so whenever okay, let's go to the easiest case. I think that will explain so much stuff. Imagine that this is the image, okay, and I decided to make it 4x2. Good. So here, all this box here, it will be one color, green. All this will be another color, red, green, red. Allah, there in between, in real life, the colors are not jumping directly from green to red. It could be some yellow in between so that the flow is continuous. Yeah. Here with this step, whenever it is 4x2, it's completely lost. So here, green, jump, red. Sometimes whenever you download some images or videos over the internet, you will see it that there are squares. Have you ever seen that? Because there is one that is missing, so they have nothing then to fill. But yeah, it means that the level of quantization here is large. Okay, so here it is giving only 4 options. Here, whenever it is 4,000, so the same image is divided into 4,000 smaller slots, okay, pixels. So now you can make the color to be closer to true color. You have here, this is green, a bit lighter green, a bit lighter green mixed with some red, and so on, so that you will see it as a perfect flow. And then whenever you look to the image, you say, wow, true color. Good. Or the resolution is very high, which means less quantization error. Clear? What is the draw? Okay, good. Good so far? I want to download an image from the internet. You will download it 8K, 4K, or 0K? You will download 8K? 4K? So, depending on what is the screen, depending on what is the connection that you have, it is not the same. If you are at home and you have Wi-Fi open, okay, you can download whatever size you want. Rather is that you have a prepaid plan, and whenever you connect to the internet, it is charging you, for example, on your mobile phone. So here you will not download the 8K. Even whenever you look to YouTube videos, okay, they will give you the option of low quality and high quality, right? If you are watching on connecting to 4G, okay, most probably you'll do it low quality. It is faster and it will consume less, okay, especially if it is a prepaid. Okay, if you are at home, what is the largest? You can download it and it's fine. Clear? You see the difference? Okay, so here, whenever then increasing the pixel, yeah, it is very good in terms of resolution. The quality is more, but increasing the pixels, okay, it can decrease the data rate, because you have a data rate, so it will take more time to download, okay? It might increase the cost, depending on how you are connecting. So increasing the number of pixels not necessarily is always a good option. The required data rate. Good that you said. So here I said it, but I didn't put it. It will increase, yes, but then you will feel that the data rate that you have is lower. With the same connection, you say, come on, what's happening? It's very slow. It's not very slow, but whatever you are downloading is heavy. وصلت؟ You said, so I thought that you realized what's happening. Yeah, good.
Which one has high quantization level, the top one or the bottom one?
High quantization, which is the top? This or this? So here, this one has higher quantization levels. Here they are 4,000 or whatever. Okay, here we have only 4. This has a low quantization number of quantization levels. This is why if you search any place, what is better, to increase or to decrease the quantization, you will find books or papers telling you it's much better to increase the quantization based on what is the application that they have. Others, they will tell you it is better to decrease the quantization. And here you come and you say, for our application, this is what we have to do. Cool. Have you used ChatGPT? Hmm?
Not bad.
Okay, good. Ask you today, okay, a question. What is better to do with the quantization levels? Homework, Laila. Next Monday you will tell me. You all use ChatGPT here? What?
Also can write code,
Yes, for sure.
but not accurate.
But يعني, it's good so far.
ما تقدر تعدل عليه شوي بس خلاص.
But yeah, good. يعني, I guess that the new releases will solve this issue. So the job for the programmer, it will be in danger.
It only deals with text.
It will come, don't worry. Google will release one soon, similar to ChatGPT. Sorry?
Oh, sorry.
Good. Done? Can we continue? So, conclusion with the quantization level with the, and it is, and we don't have a conclusion, okay, if it is better or worse, but you as an engineer, you should know what are the advantages, what are the disadvantages, and you should be the one who will tune, okay, based on what is the requirement. They will tell you, well, the maximum data rate that you can consume is this and this, okay? You check Nyquist, then you will know how many bits you can use. Based on that, you will know how many quantization levels, okay? So the question on quantization, usually it is reverse-wise, okay? They will giving you the allowed data rate, okay? And they will tell you, based on that, calculate how many quantization levels. Good? Interesting questions, okay? In the book, check them. There is something else, okay? Whenever you would like to download. I can explain this more in detail. I think I didn't forget anything. From the book, let me see, properties, non-vertical, oh, good. Where is it? Where is it? I put it here, but I didn't continue. So, at the receiver side, and we always know that whatever you do at the transmitter, you have to reverse it at the receiver, right? So that whatever you say, hi, how are you, you will listen it at the other side. So here we have what we said here, sampler, then the quantizer, then the encoder, source encoder, right? This is at the transmitter. At the receiver, what is the reversal for the sampling? I told you even last time. Interpolator. What is the, we already saw, what is the reversal for the source encoder? We have already seen how, I briefly explained, you have 0, 0, 0, 0, 1, 0, and how you can know what has been transmitted, because it's straightforward. Now, what is the reversal for the quantizer? They have not invented that yet. Let me explain here. What is the reversal for the quantizer? Good. Whenever you have at the transmitter, and what is the example that I put here? How much was it? Was 0.51. Okay, good. So 0.51 you quantize to be 0.75. Because here all the values from 0.5 to 1, we will quantize them to be 0.75. So 0.51, 0.75, 0.6403, 0.75, 0.5908, 0.75, 0.9801, 0.75, 0.84, 0.75. All the values between 0.5 and 1, we said that we will approximate to be 0.75, right? So whenever you receive at the receiver 0.75, how you will know that whatever has been actually transmitted was 0.6403? That's it. It's impossible. So here we have an infinite number of options that we will approximate them to be 0.75. Whenever they are telling us that it is 0.75, it is no way that we will know what was originally the signal. This is why there is nothing called dequantizer. The quantizer has no reversal. And this is why there will be always an error. Okay, so here the quantization is not reversible. You cannot. Okay, you will not know what was the original value. Clear this point? Good. Another property that is written in the book, maybe it could be helpful. Okay, so is the quantize. Okay, good. You can write and I will talk later. No, okay, good. The procedure is, so here, this is transmitter, this is receiver. Hussein. So here at the transmitter, I have a value here. That is any of these values. They are here. Then I quantize them. Whenever I quantize them, I approximate them to 0.75. Yes, from 0.5 to 1, they will be quantized to 0.75. Then at the receiver here, I will receive 0.75. Is there a way to know what was the original one? This is why I say it is not reversible. Always the error that you will make in the quantization will continue with the whole system. And you cannot get rid of it. Even for fixed. Whatever you do here or here, this 0.75, whenever it's here, there is no way to know what was the original one. This could be, well, this is one of the reasons whenever you talk over the phone, it is not 100% accurate. Okay, you see that the voice has changed a bit. Okay, you see that some letters are not clearly identified. Why? Quantization. حاسه بكتب شعر الآن. ليش تكتب بالعربي؟ Okay, fine. Okay, good. Go ahead. Continue. Whatever is suitable for you, it's fine for me. Good so far? Can we? Okay. Is this operation linear? By definition, what is a linear operation? Perfect. So here, the linear means that whenever here there is an increase, here at the output there is an increase. So the question is, the quantizer linear? Notice that here is the example. From I increase from 0.5 to 0.64. Has it increased? Yes. The output has increased. The same. So here the quantizer is non-linear. You can tell me maybe it jumped from one interval. Yeah, it could be. But also I can put you an example that here from 0.59 to 0.98 has increased and the output has not increased. With one example, I can prove it is non-linear. So the quantization is a non-linear operation. What does that mean in terms of for the system? No.
يعني هذا الاشياء درسناها في السلسله راح تضبط عليها لان كلها كان
In sensors?
in signal.
What you have studied in signals?
Fourier series و Fourier transform لازم يكون system linear و time.
Okay, good. LTI. Yeah, but here the quantizer, we don't need to apply a Fourier on the quantizer. But this stuff does not apply on the quantizer. Where you will apply Fourier? Okay, good question, Tab. Why you use Fourier? What is the main purpose of Fourier? That's a transfer time domain to frequency domain. So unless I want to transform time domain to frequency domain, I will never use Fourier. By the way, this is a question on the exit exam. Why you will use Fourier? Anyone here did the exit exam? Not yet? Yeah.
February 15th.
Sorry?
February 15th.
February 15. Wow. Okay, good. Good luck. Thanks. So, yeah, one of the questions, maybe you will see it there because it is randomly picked. Okay. So one of the question is when you will use the Fourier, what is the benefit for Fourier? It is to see whatever it is in the frequency domain. You have a signal in the time, you will see in the frequency. If you want to see what's happening on the frequency, you will use Fourier. Good, because maybe in time you cannot deal with the function. So if you move it to frequency, maybe it is easier. Cool, clear. Okay, good. So whenever the function is non-linear, the only issue is that its implementation will be more complex. Good. So the code, okay, that whenever it will run on the processor, it will be more complex. This is the only point. So here, non-linear, it means that it is more complex on the processor. How? We will not go into that detail. Computer engineering are in charge of that. Cool. Clear so far? Questions? No? Okay. We have two kinds of quantization. Something that is called uniform and something that's called non-uniform. Okay. So what is the uniform quantization? We have an interval from 0 to 10, for example. So what I will do whenever it is uniform, equal, so here, uniform equal length, what we call them levels, quantization levels, quantization levels. Cool, easy. This is the straightforward one. Okay, so the values will change between 0 to 10. How many levels I'm allowed to do? 10, I will divide. 8, I will divide. Whatever is the value, I will divide equally. This is why equal length. So then the other one, the non-uniform, why I will need the non-uniform? So here, the non-uniform, definitely it is non-equal length quantization level. So from 0 to 10, I will not make them uniform. So why? It's only just because I want to have a headache for the programmer. Why I will not make them uniform? They said that depends on the probability. Good. What is the, you have seen, you all here finished probability and statistics, right? And you all passed, right? What was the PDF and CDF in probability and statistics? What was it measuring? Yeah, good. So here, whenever we say, what was the two most typical examples of PDF? Whenever it was Gaussian distributed or whenever it was uniform distributed. So whenever it was Gaussian distributed, what is the idea of PDF? It is telling you that this sample, which one? Let's see here, 5, 6, 7, 8, 9, 10, 4, 3, 2, 1, 0. So the sample 5 is repeated a lot, so its probability is large. The sample 7 is probability low. Sample 10 is very low probable. Good. Then they said, and they came and they said, okay, top. Why we will give the same probability, the same quantization levels to high probability or to low probability? This is the idea of non-uniform. Where is the application? The application is the MPEG standard or the JPEG standard. You know them? No? Good. Whenever you download an image from the internet, what is the format for that image? The JPG is the JPEG. Okay, so the JPG is the JPEG. Others, TIFF, MBP, and so on. So all of these are different formats to download. What's happening? Yeah, anything that's, you miss anything? Hudhaifa? Yes? Yeah, coming, just in the example, I think it will be clear now. Okay? So the collection of images is a video, which is the MPEG, right? Okay. The idea with the MPEG standard, and this is how the standard works, is that they will learn how. Imagine Hudayfa is video recording the lecture. Okay, first of all, he will be recording you. Where the camera will be directed to whom? To here. That. So whenever it is directed to here, let's make an image. Okay, what will be from his camera? So here, this is wherever the screen, wherever his camera is shooting. Okay, so there is a table here. There is a guy here explaining. Okay, and there is here a whiteboard. There is here a speaker, another speaker. What else? That's it so far. Good. Question. The speaker will move. This other speaker will move. The table will move. This guy will move. Yeah, maybe I'm moving around. Good. Whatever is on the whiteboard is changing. Good. So if you would like to go for what is important in this picture, let me change the color. This area is changing at all. This area not changing. This area not changing. This area not, well, حتى هون nothing will change there, right? Or here, or here. So only this guy and the whiteboard will change, right? So the standard came and they said, okay, طب يعني why I will transmit this data if it is all the time the same? What I will do, I will transmit it only once at the beginning, okay? And then whatever I will transmit will be the area that is changing, which is this one, okay? And from time to time, every second, every minute, I can do a refresh, okay? And send it again, this one. That is assumed to be not be sent. Based on what they did that, this is the MPEG 4 the standard. So this is the MPEG 4 standard. This is the one that is used, okay? Whenever you download a video over the internet, it is using this standard, okay? So whenever they will make the video, they will say, yani, this way I will save bandwidth and so on, and I will optimize the system. So based on what the system will work, and let me change again the color. Which color now? Okay, they will say the probability of everything here to change is large. The probability for the red ones, low. Okay, so based on that, they will check what is the distribution, PDF. Okay, and they will say, here for this same one, imagine that here this is the area of the instructor and the whiteboard. No, let me make it even worse. Okay, for this same case, here the PDF will be like this. Yes, so here the probability that there is a change on this area that is in purple here, it is large. The probability that is to be any change in the area that is in red, 0. So the question is, and if you would like to quantize here, why you will waste quantization levels or bits on this area and this area? The same here. Why you, because this one came from here. Why you will waste resources to transmit this or this, who do the quantization, or the coding, or bits allocation, or blah 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 for all of this area if it's not changing? You send it only once. After that, you don't need to send it. Okay. What is important is whatever is changing. Clear? Clear this point? Motivation clear? So based on that, question? Sure.
How can we relate this to the non-uniform quantization?
Mahalla coming. Okay. Based on that, there is a PDF here. This PDF now, how I will do the quantization if the interval is from here to here. Again, this is the same interval. The values can change from this value to this value. But now I will do the quantization like this. So all of this, one interval, another interval. Here the probability is larger than here. And so on. So you see here now the quantization levels, they don't have the same length. This one very lengthy compared to this one very thin or short. Why? Because they will tell you that the probability of something to happen here is very low. فخلص يعني approximate all of them to one single value. I don't care. But here the probability to change is very large. So I don't want to approximate a lot here. I want to do the least approximation. And this system how many I put? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Fantastic. If I do it here with this other one, with the uniform one in blue, also I will use exactly the same amount of bits. The blue one and the red one, so here this is uniform, this is non-uniform. Both of them using same amount of bits, same that required data rate, same cost and everything. Which one would perform better? The red one. Why? Because it will capture more what is actually happening. Okay, here the blue one, it more or less it is a dumb scheme. Okay, because here it is consuming resources on something that is not changing. Clear this idea? So this is the point behind uniform quantization and non-uniform quantization. Good يا عبد الغني. شكلك sleepy ولا boring lecture.
Using this quantization will decrease the cost, or
Here, both of them, they are using exactly the same number of quantization levels. So the cost is the same, the required data rate is the same, consumed bits are the same. Good. What is the difference is that the non-uniform quantization is capturing the important part more than the uniform one. So the resolution, the performance, if you look to a video that is made of uniform or non-uniform, the video that is non-uniform, you will see it much better, because what's changing? This part. Whenever you look to the class recording at home, you will check what's happening with the speaker. Even yourself, you will not look to it. Even it is on the image, you will not even give it any attention. You will give attention to what is here, right? This is why you will see that the quality is much better than the other one that gave importance to that one. It's not the same.
هذا السوداء في بعض الفيديوهات لما بتطلع مثلا خلفيه سوداء بيكون فيها زي الشيد الاسود غامق وفاتح.
That's it. Yeah. This will be seen whenever it is low quality video. بيكون missing frames or missing packets. Okay, over the internet they have been lost, but they were replaced by black rectangles. Good, Abdullah. You follow us? Abul Khil. Sure? No issues? Hamza, what's your problem? This one? So, this is the data. Okay, this is what is really changing in the data. So here, this part not changing, this part is changing, this part not changing. Okay, so whenever I would like to transmit, the first option, if I use the blue, I will say that I will give this interval, this importance, this importance, this importance, which is quantization level. Then they came to set up, why you are giving importance to this one? It is not changing. The probability to change is 0.00. So waste. This is a waste. Okay. Then they said, okay, instead of that, give them only one interval is enough, and give whatever you save here in bits to this part that is changing. That is what is actually you need. So it is the same, the image, whenever you would like to download. If you do it over this or over this, it is exactly the same size. It will consume the same amount of bits, same data rate and everything. But this one, if you look to it, you will see that this part here is very clear, this part very blurry. But you don't care because this is what you want. Okay? Well, if you do it uniform quantization, you will see it all equal quality. So here, this standard is smart because it divided the image into important and non-important.
that's the uniform.
This is exactly of non-uniform. Okay, because it divided. If it has not divided the image, this is uniform. It will deal with the whole image as one single entity, everything the same. But this standard says, no, not the same. This part is more important than this part. If it is something more important than other, so it is giving it more priority to change than the other. This is why the non-uniform is better. This standard is the best example on non-uniform quantization. Clear? Sure now? Clear to all? So, conclusion, what is better? Uniform or non-uniform quantization? غلط. On what? Good example.
الصوت ما نحتاج.
Sorry?
الساوندز ما في شيء اسمه important و non important.
لا, there is. The sound image, the sound signal, it goes from 0, well, not 0, 100, depending on the human thing, okay, from 0 to 20,000 hertz. Okay, if you take your signal, you start talking on the oscilloscope with the mic, this will be your voice signal, okay? You shout, you do whatever, okay? Your voice is squeaky, very bassy, okay? So here it will be like this. Clear? Whenever they would like to send the signal, they said that everything from 100 hertz to 4,000 hertz is actually what is important. All stuff here, it is not that important. They have analyzed the signal. This is why our mobile phones, whenever they will send, they only send from this part to this part, and all of this is neglected. It is not even transmitted. This is the reason why, if you would like to hear special letters, okay, for example, they would like to give you the code DT3FWH, okay, so then how it will be this one? You will tell me, this is why they invented B book, D Denmark. Why? Because B and D, they will sound the same. Okay, whenever we talk B and D, they sound the same. No, they don't. But because they have thrown this part away, some letters B, D, T, okay, the difference between them, because the characterization of these letters is in this part, it has been lost. So in voice signal, immediately they apply this. I need an example whenever you cannot apply non-uniform. Uniform is better. Camera shaking, not, but moving camera. So whenever you are moving, with the camera is moving, you cannot say what is important, what is not important, because you don't know. Okay, everything is important. So uniform quantization is better for moving camera. Another example here I heard. What was it? The match between Al-Ahli and Real Madrid. غلط. Okay, depending on what, based on what. So here you are shooting for the inside sorry, مش فيلم. لا, you said the match. Yeah, match. Okay, so whenever you are making the picture of the soccer field, are you just, okay, the question is, this is the soccer field, okay, the goals are moving. What's the importance of sending always the same image of the goal? It will not move. Okay, so here, depending, whenever you are zooming only on this part, you are zooming on this part, or you are making the picture of all, because here even this is the soccer, okay, around it here, it's usually nobody is moving, so you will not care. It is again, it is, you are zooming, not zooming. Okay, so if you are zooming, then all of this area is important. Okay, not zooming, then this part is not important. Then the system is dynamic. Okay, it can switch between non-uniform to uniform quantization. Hamza. The human eye non-uniform. There is no quantization for the human eye.
For example, I'm trying to focus on you, but if I'm trying to read something for me, it's impossible.
But not with the same.
I cannot make it the same stuff. Another example, whenever you cannot use non-uniform. Sorry? Sensor? What? Completely the opposite. You are saying this is an example of uniform. Yes. So here, whenever imagine this is a surveillance camera. Surveillance camera. Here you are putting you are shooting, okay, and this is for surveillance. You will know that the thief will come from here, will from here, will from here, will from. You don't know. This is why, in this case, whenever it is for surveillance, you will deal with it uniformly. Everything is important. Okay, you cannot neglect any part like we were doing here.
What if we have a sensor that works with motion and surveillance? Like it's not working, and then when there's motion, it works. The camera. I think this.
All the sensors are like that.
No, like some cameras just keep like shooting.
Keep recording? No. Okay, so whenever it is a sensor that needs to record and just keep, okay, they will use this technique that you are saying, okay, continuous recording, okay. But whenever it is something that is transmitted, no, they will do it based on action. If there is activity, it will move. Perfect. This is the best example, okay. So radar systems, okay, they are shooting here, okay. They don't know where is the plane coming from here, especially if it is military one, okay. You will not know where is the enemy coming from. So whenever the radar system, it has to give importance to every place. Here it has to be perfectly uniform. Here, uniform. Clear? The example is clear? So again, uniform is not better than non-uniform. Non-uniform is not better than uniform. Based on what is the application, what are the requirements, what is the constraint. Maybe there is no constraint, okay, on the data rate. You can download infinity. I don't know. Okay? So based on that, you have to decide what is better, uniform, non-uniform, and so on. Clear? And this is this is always your role as an engineer. Yes, go ahead. That's it. So even the standard, the MPEG 4, it's hybrid. Okay. Maybe you are moving with the camera, so it cannot be non-uniform. It has to be uniform. You stop for some time, okay, and it realizes that he is not moving, then he can be removed. It will go non-uniform. Answer? You were raising hand.
لا
والله كنت raising hand. يعني ولا you want to leave?
لا أنا الساعة هنا يعني مش مطلع الساعة.
I was going to stop, man, but because of that, no, we will continue. Questions? Sure. Let's recap. Okay, well, there is a new subsection called PCM. I need to explain its motivation, but yeah, now I will do just the recap, and next time I will go more in detail. So we have seen uniform. No. We have seen fixed source encoding. When the fixed source encoding was suitable, when it is optimal.
Same probability.
Whenever we have same probability. So here we have equal probable samples. And we have the other one, which is the variable source encoding, whenever they were non-equal probable samples, right? Now that we have seen the quantization, I can explain the third option, okay? So here, both of them, and I have not said it before, now we can say it because we will see the other one. Both of them, they will only run if they are equal probable samples and they are IID. What is IID from probability and statistics, يا حذيفة؟ أنت حمزة؟ يا حمزة. حذيفة. What is IID, صالح؟ عبد الغني. ما شاء الله. يعني إذا هيك after you graduate from here after 2 years we will call you back, we will take the degree لأنك من زمان أخذت الستاف. That will not work. أحمد. Guys. IID. أبو عسل. No. his colleague, Amir. Amir, right? Amir. Your name? Abdullah? Abdullah al-Masri. Abdullah. Okay. What is IID? Yeah, you should have seen it, okay? No, I'm sure you have seen it, okay? Is independent and identically distributed. Okay. So here, yeah, probability. So here, PCM, I will explain whenever it is non-IID. I will stop here. I have to extend then what is IID so that I motivate what is the motivation for this new subsection, the PCM. I will always assume that you are, so many assumptions, the best in math, or best in physics, or best in programming, or best in what, signal and system, or probability, or circuits. Sorry? Not memorization, knowledge. فلاح الهندسة. Okay, good. Questions? We will stop here, and on Wednesday, no, today Wednesday, right? On Monday, inshallah, we will continue.